And welcome to the International Water Resource Association webinar on how water improves agriculture, advances in climate responsive irrigation for sustainability and productivity. We also want to take the opportunity to apologize for last week when we experienced some technical difficulties. And thank you very much for joining us today. So just a very brief introduction of our panelists today. We have Dr. Valeria Lima, who currently works as a research scientist at the Department of Primary Industries and Regional Development in Western Australia. Her current research focuses on improving fruit and vegetable production systems and irrigation water management at a regional level. Her interest in crop and water relations started as an agricultural engineer in the semi-arid region of Brazil and was expanded during her PhD in plant-based irrigation scheduling in Australia. Then we have David Iyer, who is the CEO of the Future Food Systems Cooperative Research Centre, CRC, which is a national research group funded by the Australian government and over 50 industry and research partners. His career has spanned the energy, water, and agri-food sectors with a focus on developing STEM-based solutions to complex industry development and sustainability challenges. Our panel will also include Professor Greg Leslie, who is director of the UNSW Global Water Institute and a professor in the School of Chemical Engineering at the UNSW Sydney. Professor Leslie specializes in systems analysis for water and wastewater treatment processes for municipal, industrial, and agricultural applications. Prior to joining UNSW, he worked in the public and private sector on water treatment, reuse, and desalination projects in Australia, New Zealand, Singapore, Hong Kong, and the United States. Professor Leslie will also be moderating today's webinar. So Professor Leslie, if you'd like to make a few introductory remarks, that would be great.
Thank you very much, Nirvana, and welcome everyone. Thank you for participating in today's webinar. We're looking at the very important issue of how water enables agriculture and how the demands placed on agriculture by a growing population are only going to exacerbate some of the problems that we have in managing water. And so we need to take a very integrated look at this. We can't look at the two problems separately. So the speakers that we've assembled today are going to canvass this issue from a systems perspective or a policy perspective from the top down, and that will be led by David Ayer, who, as Nirvana said, is the Chief Executive Officer of the Future Food Systems CRC here in Australia. And David will be providing a regional specific example, but the issues and the approaches to managing both water and food systems in Australia are applicable in other jurisdictions. My former colleague, Valeria Lima, who is based on, I'm based on the east coast of Australia. Valeria is based on the west coast of Australia in the Department of Primary Industries and Regional Development in the Western Australian government. We'll look at it from a precinct level, how areas can be managed, particularly using indoor cropping technologies, but other cropping technologies to enhance the volume of food that can be produced per unit area and per unit volume of water. And then to close out, I'll have a look at a technology-driven approach to water management, but one that was developed with how to extract value from both marginal quality water and marginal quality soils in a climate responsive way that is easily accessible in both developing countries and developed countries. So there'll be our three themes, and we hope it stimulates some conversation and lively questions at the end. So with that, it's my pleasure to hand over to David, and I'd invite him to share his screen now.
Thank you, Craig, and hello everybody. In my presentation, I'll really look at a high-level systems view of how to improve water systems. To achieve success in this area, you need technology, politics, and economics. So a systems approach really entails, yes, smart engineering, but also industry engagement and a really strong operating environment. In other words, the actual places where water reform needs to occur. So today I'm just going to quickly go through a bit about what our Cooperative Research Centre does. I'll give you a high-level overview of water in Australia. It's been an interesting number of decades here. Some of the solution areas and potentially some discussion. I think we're going to keep the discussion for the end of the session.
David, if I could just interrupt for a sec, do you want to just put your slides on presentation mode? You're sharing them fine.
Oh, I see what I'm doing. Thanks.
Yeah. Just that's all right. No problem. Perfect.
Yeah. So the Cooperative Research Centre is a strategic program funded by the Australian government. There's a quite large budget over 10 years. We commenced in 2019. We've got nearly 50 industry, government and research participants, including 6 Australian universities. We provide to our participants access to leading researchers and high-tech laboratories, and it's really focused on place-based innovation. And we have 6 participating food clusters around Australia. These are regional areas which have high volumes of agricultural production and are looking to improve their ability to value add their production. Someone mute themselves here, please. We've got a very ambitious industry transformation agenda, which really entails bringing STEM technologies and circular economy solutions into the food sector, from farm all the way through to consumer. And it entails smart regional specialisation, helping regions understand what they can best produce, most sustainably, most profitably, how they can really grow prosperity and sustainability in their region. And part of that is taking a demand-driven approach to production in our target food segments. In Australia, we tend to grow things and hope to sell them. We're trying to flip that around and grow the things that the market really needs. So our key concepts are adding value to and differentiating primary production, or what farmers are growing, connecting a value chain, getting farmers to commit supply to upstream processes, Industry 4.0, really bringing advanced technology into both primary production and food factories, sustainable development, which underlies everything, really having food systems respecting limits to natural resources, minimise waste and increase economic return. And of course, the limits to resources in Australia are quite severe. And as I said before, regional clusters, which is really about structuring collaboration between industry, research, government and community at the local level. So actual people are working together to transform food systems. These are our target segments. These numbers are about what the Australian government's projected being the scale of global demand by 2030. So premium foods are healthy fresh foods like meat, vegetables, fruit, free from fruits, foods for allergy sufferers, organic, that sort of thing, and targeted eating, which is a massive growth segment as food starts to intersect with medicine and where you start producing functional food products. We have 3 programs in the CRC, Planning for Sustainable Growth, which is literally about the physical planning and connecting everything up, infrastructure, government programs and circular economy for wastewater, energy infrastructure. And we've got our food clusters emerging around Australia, which are orienting themselves this way. Here's an example. We're working with a very productive region in New South Wales to try and bring in new food factories, smart energy solutions, and most importantly, sustainable approaches to water, because water is a critical limiting factor if you're wanting to start to process food in a regional area. Our second program is about intensive indoor production, very important in Australia because of limits to water and a highly variable climate. So Australia's putting quite a bit of effort into protected cropping, and Valeria will be talking about that later. But one of our aims is to reduce reliance on imported IP and technology. At the moment, most of the greenhouse technology in Australia is imported from places like the Netherlands, and the whole system is oriented to a European climate rather than to our climate. So some of the work we're doing with partners are in areas like sensing technology for phenotyping, smart films for greenhouses to regulate our rather harsh light, and projects really focused on optimizing water energy and chemical usage within protected cropping facilities. Program 3 is where it all comes together in future food products. So we're providing expertise to commercial companies like Sanitarium Food around how they're going to design more sustainable and valuable food products, but products which are more nutritious and which have very high provenance credentials and also sustainability credentials. And part of that is scientifically based formulation and scientific claims around the functionality of food and its actual quality. And we hope Australia is going to be a world leader in sustainable nutrition. So, water in Australia, our theme today. Most of you probably know this, but we have one of the most variable climates in the world. It's a land of drought and flooding rains, and we have very low mean rainfall and very high rainfall variability. And you can see some data here and some pictures. This is a country town in Australia. One moment it can be flooded as water moves across the inland, which happens at maybe 3 or 4 or 5 years. But a lot of the time it's in severe drought and the soil is literally being blown away. It is a very difficult environment. So it's a largely flat continent. We have few mountain ranges, very few good dam sites. Floods move very slowly across the inland, which means we have very high evaporation and water loss. We have poor, fragile soils and very little arable land in general. And the coastal zone has better soil and water, but is dominated by housing because that's where our population lives, particularly on the east coast. So the lowest point in Australia is Lake Eyre, named after one of my ancestors. It's 15 metres below sea level. It very rarely fills, and its water is hypersaline. So that's what a big lake looks like in Australia. Now, given that our water is so constrained, over the last several decades, Australia's been through a major reform process around its water policy, and that entailed assigning water entitlements to farmers and establishing very complex rules around allocation and sharing between users and the environment, and also establishing SCADA systems for measuring, monitoring and regulating and trading water. And some of that policy has been exported to other nations, and Australia has been a leader in this policy domain. Our policy work and our reforms have been focused on the Murray-Darling Basin, which is this light blue area here, which is Australia's biggest river system. And 66% of Australia's irrigation water use occurs in this light blue area. To give you a sense of how flat this continent is, when water's moving from the north up here down to South Australia, the Murray River flows through here. If you can see my arrow, there's about a 1 degree fall from the top to the bottom. It gives you a sense of how slowly rivers move and how little water flows through them. Kind of a polar opposite of a river like the Amazon. As you would expect, with water so scarce, it's a source of very significant water allocation conflict in Australia. Farmers and irrigators and country towns are dependent on irrigation water, but at the same time we have a fragile environment which needs water. And of course cattle, our graziers, need water as well. So you have cropping entities, you have pastoral entities, you have the environmental lobby, and then towns themselves, people in the towns and factories need water. And overarching all of this, we have climate change driving increased water scarcity. So it's a very hot political topic in Australia. So limits to growth, chronic drought, climate change, and uncertainty around groundwater reserves, runoff and recharge. This picture here is of the Darling River, one of Australia's most important rivers. It may look like just a ditch to you, but that is in fact one of Australia's major rivers. So, solution areas. Well, our approach at the CRC is finding ways to get more value from less water. So if you take a systems approach, it's really applying things like material flow analysis and the sort of things that engineers do in factories to optimize the whole of regional systems. And that in turn entails building value chain collaboration. So farmers are growing the right things which factories want to add value to and which consumers are prepared to pay a reasonable price for. So it's quite a novel approach in a way to building a regional industrial system which is occurring within a natural environment rather than indoors in a factory. Reducing irrigation water loss is a huge issue in Australia, and part of that is piping and pressurising irrigation systems, what we call the water and energy nexus. At the moment, because electricity is expensive and scarce in regional areas, farmers tend to rely on flood irrigation or to pump groundwater at the low electricity price periods into holding dams, which are usually quite shallow, where they get high evaporation. So what we want to be able to do is to pump on demand and to irrigate on demand in piped and pressurised irrigation systems. None of that is possible without access to cheap, affordable and reliable electricity. So what we and other parties have been doing we've been encouraging the uptake of solar energy in particular in regional areas, in our major cropping areas. I know this farmer, for example, that's a 100 megawatt system, and he's lifting massive amounts of irrigation water from his groundwater systems. He lifts them about 100 metres. So his peak load in midsummer is extremely high, and that puts pressure on the regional electricity distribution system. So it's really beneficial for him to go off-grid, generate his own electricity, and then he can pump on demand when he needs to. So really, to solve water in Australia, we need to align water and energy infrastructure, and it's a first order. Both of these are first order national security issues, and both energy and water reticulated systems. There's potential for distributed generation, microgrids, local generation of electricity, and really it's important for Australia to think quite differently about water and energy services at both regional and national level. So central to what we're trying to do is sustainable food precincts, which is connecting up complementary facilities and stakeholders at regional level. That means that you can share the OPEX and the CAPEX around building things like water recycling plants. Individual factories are going to find it hard to do that, but if you share this infrastructure, suddenly it becomes much more affordable to take a sustainable approach. So it's thinking about water, energy and materials in a whole of system way. One thing which Australia possibly needs to do is manage its east coast floods a bit better. Ironically, in the inland it's very dry, but on the eastern full, this eastern side of Australia, you've got moist air coming in from the Pacific, and when it hits the mountain range, it just gets dumped onto the coastal areas. And those floods cost billions of dollars, but we're not harvesting that water efficiently, and we're not redirecting it inland, or we're not using it locally as efficiently as we could. So there's interesting potential in Australia for some smart engineering solutions around micro dams and innovation in our water harvesting right policy, which doesn't really accommodate things like micro dams. Valerie is going to talk about controlled environment production, but we see this as a hugely important thing for Australia. You may think there's a lot of land in Australia, but our population is concentrated in our major cities, and it's quite important for us to be able to generate fresh food within those cities, close to the demand centres for that food. So we do see a big market for indoor cropping technology in Australia. It's minimal at the moment, but we see growth in this field. So that's it for me, Greg.
Thank you very much, David. That's a great overview of, well, first of all, some of the tensions around water availability and supply in Australia, but also vision for linking water, energy and food production. We've received a couple of questions during your talk. What I think we'll do, because some of them relate to what I believe Valeria is going to cover. But David, do you want to expand on the use of linking in your precinct model, linking wastewater and other systems, the recycled water into food production? Do you see any barriers there?
Part of it is perception. It's possible to build a sophisticated factory in a country town without increasing the load on the water system. In other words, it can be run entirely with recycled water and through internal recycling of its water use. Process steam, for example, is very important in food production. But if you implement the technology right, that shouldn't increase water allocation conflict. But of course, the community have to understand that. So one of the things we'll be doing in the next couple of months is organising a workshop in one of those country towns, just to bring the community along with this notion that smart engineering can help solve these water allocation problems. The other barrier is really helping farmers to grow the right thing for evaluating in that particular factory. And that right thing, whatever it may be, needs to be identified through analysis. And that right thing may well be a lower water demand crop. For example, the pulses may require less water than another crop that's been grown in a region. And if you're going to build a major textured plant protein based factory, suddenly that becomes an end market for the farmers who are growing it in that region, which is what I mean about material flow analysis. If you really think about what you're going to grow in terms of its inputs, water in this case, but also energy and agrochemicals, then you can start having an economic analysis of what the best value use is of those inputs to produce the maximum economic return to that particular community. And that's where you bring the whole community along with it.
Excellent, thank you. We've so introduced Valeria in one sec, but I just note we have one comment. Sorry, one question that wasn't written down. Tony Slatcher, did you want to say something specifically? Nope, had the hand up. That's all right. The other question that we got there was around water demand for specific crops, and I think Valeria, you're going to touch on that with your presentation. So that's a great opportunity to throw to you now, Valeria. Do you want to share your screen?
Yes, please. Can you see?
That's perfect. If you just now put it on project, that's it.
So can you see the main, just the presentation, or next slide, previous slide?
No, we're seeing you in the presentation. It's perfect.
Perfect. All right. So hi, everyone. Thank you for having me as part of this webinar. So I'm Valeria Almeida Lima, and I'm a research scientist with the Department of Primary Industries and Regional Development in Western Australia. And today I'm going to be talking to you about two main things. One is a report, a CSA report that it was done like in the previous months, but it's a really good related with the protecting cropping work we're doing in Western Australia. So the report will be focused on the interests and opportunities for the protected cropping in Australia as part of the Future Food for CSC. It was a survey with the participants of the CSC, and that would help to guide the future activities, research activities of the CSC project. And I will be also talking to you about the protected cropping and irrigation water management work that we're doing in Carnarvon, north of Western Australia. So the Future Food CSC Participants Survey, it aimed to assess the local industry needs and their wishes as well for future facilities and technology in protected cropping. So the participants considered in the survey included commercial growers. So what was the challenges that we're facing on growing the crops, companies capable of designing and supplying protected cropping infrastructure and equipment in Australia, because that's one of the aims, to reduce the reliance we have on imported technology. And also we have the Australian universities so we had the regional councils and organizations and the Australian University, which would touch on how to develop technology, on research, but also how to deliver that technology to the growers as an extension at the regions level. So the participants' interests were categorized into 11 groups, as you can see here, going from general facility management and design as the first priority, and that was just a general interest. In second comes water efficiency and recycling, which is really relevant to the this webinar today. And in third comes, I think I would collect together the lighting and climate control and IoT and automation. Some of the technologies include the three of them together, which combined comes to 33%. So just to look a bit closer to those categories of interest, in water efficiency and recycling, which reflected 12% of the interest, we had irrigation, water monitoring, and automation. So the main interest in here was, for example, in closed systems, glass house, how do you monitor your water quality? How do you automate that? But just like technology, that looking forward in future, how would that allow me to be fully recycling my water, monitoring the water levels really close in a way that I would just top up whatever has been uptaken by the plant, and I didn't need to dump my water and restart a new fertilizing irrigation solution. So there's also a push to develop or to progress on plant-driven irrigation scheduling. Most of the farms and irrigations, they would look into the soil medium water content or the soil water content in the field and base that the irrigation program on those variables. But now there's a push into looking into observing how is the plant responding to the environmental conditions, and can we time irrigation on when the plant is actually showing its stress. So there is a few equipment in the market that looks into that, but also what the industry is really looking forward as to equipment that not only gives you data to base your decisions, but are technology that takes up the data, process that for you, and make up quick decisions. So in a way that the system is always operating in optimum efficiency. So touch base again on nutrient levels for closed system and wastewater recycling as well, especially like I've always worked in a semi-arid environment. So water is really precious. So how do we recycle our wastewater, treat it in a safe way that we recycle in the water, but not only that, in agriculture, the nutrient content of that wastewater or leaching. So coming on the general facility design, which accounted for 19%. So it was not specifically a specific design. So the participants just listed their interests, and then it was in the category of general facility design, which included vertical farming. So people were interested in hydroponics, aeroponics, improved design to maximize natural ventilation in hot climates, combining shades, evaporative cooling. But there's a few technologies or a couple of technologies available for reducing that heat in protected cropping. But one of the challenges is the amount of energy you spend in those systems. So I think what we were looking here is some new designs that were coming forward, specifically designed for tropical areas or hot climates, and in how can you optimize the design of the structure to reduce your energy requirements. So one of the available technology are fogging, but that's dependent on water quality as well. So for example, in Carnarvon, we have sprinklers that is on top of the inside of our net house, and we use it. The plan was to use it to cool down, to increase the humidity and reduce the temperature inside the net house. But also it was limited by the buildup of salt on the leaves when we use that once, or for a period of time. So now we have to go back and reanalyze the water quality to see if certain systems are suitable for certain conditions. Cooling pads, heat exchange. So there are also technology looking to glass panels with wavelength selective design in a way that it would block the rays that would increase the temperature inside the structures, but will also let the right spectrum of light pass through to the plants. So those, I think, it's a very promising technology if we can get that. And in some of them look at the different colors, but also the see-through ones, the transparent ones. The technology that emerging is really promising as well. And for the conventional ones that already exist, the glass houses, there are like glass coatings that can be used, or can we develop new glass coatings to block incoming radiation at the right spectrum? And so you can achieve reduced ambient temperature and water usage. On the climate control, IoT and automation and lighting, which combined accounted for 33%, we had so orchard protection and indoor cropping, which you have, I think a lot has been looked into the indoor cropping and a lot of technology to put into it, because the idea is to get closer to where the consumers are, to the cities. So you go into smaller spaces and higher level of technology for indoor cropping as close as you go to the cities. But also a component of it is orchard protection. How do you develop indoor cropping for orchards? For in Carnarvon, it's really important. And we have the protected cropping project in both fruit and vegetables. So that comes a bit of challenge as well. And it also reduces your ability to control that environment as you go into the orchard protection. So we have plant, soil, and microclimate integrated monitoring. That's the main aim for the in IoT and automation. So you have, instead of using several systems that don't talk to each other for plant, soil, and climate monitoring, the idea is to have one system that couples all of them, not only on the software, but couples all of them in a smart algorithm to act upon it, and the whole system works as one. So you have vents and shades, opening and closure, what current system does, CO2 supplementation, but also a big factor here is plant response to environment and linking soil and climate control to what the plant response is being to the environment. So automated light supplementation to meet the crop requirements. If you have a level of light that needs to be consistent over a couple of days, does your light adjust to the natural light to compensate for that and keep that level as constant as possible? Improve efficiency, spectrum of light system. So especially the artificial lighting is that provide the spectrum that your plants need. It doesn't recreate the sun spectrum, the full sunlight spectrum. So that's some of the challenges that we have in climate control and lighting. And the others including robotic harvesting, which is it's a big push for labor costs, especially in COVID times where labor has been a big limitation for the growers. And also, for example, medical grade crops, if you're looking into products with medical grade, it is important to have a robotic harvest just to reduce that human handling and a possible level of contaminations in the products. Robotic system for pollination, some of the bees species that are allowed in other countries, it's not allowed in Australia, so they rely a lot on labor to manually do the pollination. So looking into robotic systems that could replace that labor, it would be reliable and also like probably cheaper as well. Looking into new species that could become commercial crops, including native and indigenous crop species, looking to also into the nutritional component of those species. Sustainable biodegradable materials for vertical farming, including films, twine, ties, something that can, if you tie, nowadays you have plastic twines and ties that you use on your tomato crops, but then at the end of the day, it prevents you from reusing that biomass because you can't put plastic into some of your furnace to provide heat or things like that. So, and if you could use those materials to allow composting of the biomass at the end of the crop phase, that would be really interesting as well. So touching on the facility design, so there's a range of designs available on the market. So on the report, we also looked into what's available, but also what's coming up, what has been looked at, but is not commercially available as a way of developing new technologies. So you have roof and laterals material for control light transmission and ventilation. So there's a challenge when you have, for example, solar panels try to attach to the roof, where you can see on this picture, the first picture on the top, so your left top picture, you can see different shades on the lines where the solar panel is installed on the roofs. And that would, ideally, that would require different water regimes, because the plants getting more sunlight would require different water regime. And that's a challenge. So you have panels here for the roof and laterals that is a selective wavelength characteristic to them, including different colors. But there is also like a see-through solar panel research going forward, which looks really promising. If we can achieve that, to make the whole structure more energy efficient as well. Some of the research has been done on improving designs for natural ventilation specific for hot climate regions, including the water G greenhouses. They use heat exchange to cool, this one here at the bottom. So they use the heat exchange to cool air, recover water in the arid regions of Spain. So the NVAC greenhouse design, which is just creating that channeling for the hot air to go up and then cooling that down with a misting system. And so that was proven to reduce the temperature by 5 degrees and increase the ventilation by certain meters per second. And also there are semi-closed like module air, which this one it's available commercially, that you can assemble it with individual components to meet the needs of warm climate. So there is commercially available designs for hot climates, but it comes with challenges, and usually includes shading, irregular shading, or not really suitable for the purpose specifically. It works, but it could be improved, and there are research looking to redesigning the protective cropping. So for the remote cropping and controlling system, looking a bit more, one that is really interesting is adjustable light spectrum that can resemble a specific regional climate. For instance, important for cannabis flower quality, it's one study that came up. Automated capacity to compensate for and maintain a constant level of daily light. That is a huge thing if you do indoor cropping, to recreate that light, because you don't want the plants getting too much shady, and then you would have that vertical growth in response to that, but not necessarily increasing your yield. So there are new technologies looking into, or research looking into fiber optic system that you collect, concentrate that light outside and then transmit it indoors. So you pretty much transferring the full sunlight spectrum into indoor areas, but it's the early stage, but it holds a potential. Light features coupled to sensors and cameras for cloud-based virtual crop monitoring. And that is that's the aim overall of the crop monitoring. Real-time measurement, real-time monitoring, real-time looking into the physiological response of the plant to that environment, and a system that is there not to provide data to you, but it's a system that gives you the reliance that it will be running the data, it will be identifying the need for the change, and it will be change that automatically, but not different systems to working separately, but systems that connect together the lighting and also the physiological response, observation, the sensors connected to the plants, and that would go specific to crop species and growth stages to provide you with the best indoor cropping environment. So now I want to talk to you a little bit on the Deep Earth Protected Cropping Program at the Carnarvon Research Station. And the reason we go for protect cropping Carnarvon is the environment it is located. So Carnarvon is located 900 kilometers north of Perth. It has a semi-arid climate with an average annual rainfall of 150 millimeters. But following up with what David said, the same town can be in drought. But this year we had over 500 mils, which means that we had a flood at the beginning of the year. So how do you prepare the same town for drought, but also for flooding? So Carnarvon is it's fed by underground water from the Gascoyne River, which supplies an average 170 farms. So that each farm has a proper tile to pump water out of the river, the groundwater. And there are also different principles when the river is flowing. Usually once a year it would flow. And then sometimes it can be determined that it's a free pumping because the river is flowing. But there is also skim water available, and that is all organized by the Gascoyne Co. So the average farm size is 5 to 10 hectares. The main crops include, so it's really on most of the farms, they would have some perennial crops, so fruit, and they would also have vegetables in a way that they rotate or they schedule them stacked throughout the year. The main crops including tomato, capsicums, pumpkins, zucchini, mango, banana, melon. So most of the produce would go to Perth. Some of it would get exported, but most of it goes to the Perth market. But now there is a big drive on developing, as David mentioned as well, developing the industry to what can we sell, what can we export, what can we improve. So defining the crops that needs to be grown and going for those crops rather than growing and having issues with commercializing the produce. So the climate in Carnarvon has strong wind conditions, and sunburn usually downgrades the produce. So for example, for the mangoes, up to 20% of them can be affected by sunburn and downgraded from the premium to class 2 and really reducing the income for those growers. In terms of infrastructure at the research station, we have a 1.3 hectares net house, which is equipped with 4 different shade factors. So mostly for the vegetable project, you can compare the different shade factors for a particular crop and see what is more suitable. So we have a misting system, again, that it's dependable on the water quality. So when the river is flowing, you have a better water quality than when it's been pumped and the river hasn't flowed for 2 years or so. So you have to look into alternative system to produce water for that misting system, including desalination, probably. So in the net house, we have the fruit and perennial crop vegetables. So here we have a citrus trial, we have longan, lychees, we have mangoes, and also we have trials coming out from persimmons and custard apples. So it's a range of fruits and vegetables that we look at. And also always looking for new crops, new high value crops as well, as an alternative for the growers. We also have a crop greenhouse, which is a total of 800 square meters. We have a retractable roof, again, to open when you need ventilation, or to close. There is insect exclusion netting on the sides and on the top as well, if you want to do research into mitigating your chemical usage. So you could close it and prevent pests from coming, and also reducing the need for spraying, allowing better biological control of your trials. The crop is mainly used for vegetable trials for the space of it, and also like with identifying crops that are suitable. And how it works, again, there's a lot of the size of there's a lot of shading inside, so it's always trialing which crop works better in that environment, and how can you change the settings of the facility to adapt to your crop or to the needs of your crop. So we have a really interesting project looking into improving the productivity of mangoes through protected cropping. As I mentioned, up to 20% of the mango production in Carnarvon can be downgraded due to sunburn, wind that is really strong in Carnarvon. It would promote the rubbing between the branches and the fruit, and a marking that would reduce the appearance of the fruit. So we're looking into new training systems as well. Okay, we increasing the cost for the grower because of the net that we need, the net house. So how can we put more trees into a limited area? How can we manage the vigor of those trees when they are planted closer together? And we're looking into using like a trellis system, you know, the poles to support a net, but also a trellis system, if you see at the middle bottom picture here, to build that wall of fruits in a way that you facilitate probably for mechanized harvesting, that you improve your spray program. So it's no way of improving your yield and improving your efficiency in the system. So 10%. So our trial is planted. We're looking into 3 different varieties and how to manage the vigor, and also it's inside a 10% net house, which reduces the incoming radiation by 10%. And also we have a design for a retractable net on the outside, which instead of being constantly inside the net house, we would have a retractable netting system that would open during summer, the hotter months, to protect the plant and the fruit quality, but also for the remaining of the year when the qualities are not as extreme, you can leave it open. So we also do extension work at the growers' property to demonstrate to them, you know, how you can protect the benefits of protected cropping for orchards. So we have just overhead shade for this particular farm. We have 10 plants covered, like 2 replicas of that shade. And we do weather monitoring for, you know, photosynthetic active radiation. We do UV light and total radiation, temperature and humidity. And also we seasonally, we measure the plant response to the environment. So we can go back to the grower and say, you know, and tell him, this is the benefits. This is why you're observing less fruit sunburn under the protected structure. So we did that quick measurements on the stomatoconductors of the plants, and then shaded and unshaded just on the winter to define our methodology. And then we hope to progress that into spring, summer, and other, mainly on summer, to really go back to the grower with those values and demonstrate the importance of protected cropping. Another interesting work we're doing is identifying plant-based irrigation monitoring, which we're using stem psychrometers that would measure the total water potential of the plant, reflecting the water stress levels, and also sap flow meters. We're coupling the stomatoconductance at the leaf level with the soil moisture sensor, and we're trying to refine those guidelines for the growers, not only provide technologies to them that they could use to refine the irrigation or analyze if the irrigation is being efficiently delivered, and also equip them with knowledge on how to interpret that data. But again, you can see it's a lot of technology, but it's really disconnected. Ideally, you will need one system that it's able to picture together all of those figures, all of those variables, and provide you with decisions. And also in the indoor cropping, operate those decisions in the controlled environment. And the idea here is to minimize the plant water stress based on the variables that you can control, mostly in a protected indoor environment. So we have a long-range radio network, which we have the antenna here, and that would work for the whole Carnarvon farm area, and that the growers can use the system to access through the portal to remote data of water meters. So they are able to see if there has been a leak without having to physically be at the farm all the time. So the water quality, because especially in Carnarvon, when you're pumping, but then when you're tidal, so you're pumping based on your tidal, on your allowance, but then as your water quality reaches near 1,000 ppm, then you have to stop that pumping. So having a water quality measure that can be accessed continuously and remotely is really important as well. You have soil moisture sensing, weather station, that system that we are currently using, but there is an array of technology that the growers can use and access to that network. And that was my presentation. Thank you, and I hope I could show a little bit of the work we do in Western Australia in Carnarvon, and also a bit of the general overview of the CRC survey and the interest we have and how they too correlate.
Thank you very much, Valeria. That was wonderful. We've got a couple of questions, but I think we'll leave those and do them at the end in a general discussion, if that's okay with you, Valeria.
Yeah, that's okay.
Yep, excellent. All right, so David has given you the system picture. Valeria has now gone down to the precinct level, and I'll pick it up now and discuss the, I'll find my slides. I'll talk about the some problems around water scheduling the irrigation and dealing with saline water and poor quality soils. So just bear with me for 1 second. Okay. Is that presenting okay? Nirvana, thumbs up.
We're seeing your presenter view, not your.
Oh, I've got to switch it to. Yep. Oops. Do you think you'd be better at this by now?
It happens when you've got two screens.
Yeah.
I think you just need to go to display settings and switch view, if that helps, at the top.
At the top of your screen, there is show taskbar and display settings. Go on the arrow in the display settings. It should have an option there to switch.
Right, show taskbar. Yeah.
Now on the next one, display settings.
The middle one.
Middle one. This one?
Display settings. We have show
On the top.
Display settings and slideshow. Above the presentation, just above it. Yeah.
Okay.
Next to show taskbar.
Ah, got it.
Yeah.
Yep.
There you go. Yeah, just swap present. Yeah, that's
yep. How about that? Sorry about that, guys.
No problem.
Sure.
Okay, so look, let me jump straight into it. It's been set up really well. We mostly looked at the issue of how do we begin to redesign subsurface irrigation systems, particularly to allow farmers to grow beans. The reason we selected beans is that the common bean, Phaseolus vulgaris, is responsible for around about 35% of the world's plant protein that's grown. So it's very important in developing contexts, in developing countries as well as in developed countries. And particularly we wanted to look at how to maintain yield when you increase the salinity, and also how to develop systems where the soil is of a lower quality. And I just want to thank Bruce Sutton, who's the agricultural scientist, and Claudia Keitel. They're from the University of Sydney, and of course Valeria, who was a PhD student and postdoc that worked on this, and my collaborator in the School of Chemical Engineering at UNSW, Pierre Leclèche, who was the membrane expert. So a climate responsive irrigation system is really important because we are living in a warmer and drier climate where evapotranspiration rates are higher and availability of surface water is lower. So David has spoken about the policy and the planning. Valeria's talked about the technology. I want to look at systems that enable both subsistence level farming plus broad scale or larger industrial farming to sort of thrive in areas where there is less availability of surface water, and we need to access more saline groundwater. Now, irrigation is really important in Australia, as it is in a lot of jurisdictions around the world. In a lot of places, it drives farm gate profit. If you look at irrigation schemes in Australia, we have around about less than 1% of our total agricultural land is under irrigation, but the irrigation systems provide around about 28% of farm gate revenue, and of that, about 50% of farm gate profit. Now, most of the irrigation is surface sprinklers, which account for about 60%, which are the least efficient because of evaporative losses. Surface or flood irrigation. The sprinklers are the balance. The targeted drip and subsurface drip don't make up a large proportion. It's about 9% of our irrigation systems, but these are the ones that have the potential to use this technology. The second issue that we want to look at is the issue of saline groundwater. Now, David spoke about the Murray-Darling Basin. We're looking at a map here of the lower reaches of it, particularly around Victoria, the state in the south, where we have a pretty good band of water that sits in the slightly saline from about 500 milligrams per litre to moderately saline, getting up to 7,000 milligrams per litre. And that was the area that we were targeting, trying to develop systems that work in with that band. Now, the problem, of course, of working with salty water is you begin to reduce the yield. And we call that the root zone salinity. It's there measured in decisiemens per metre. And you can look at some of the crops that we've been interested in, apples, almonds. I'm going to talk specifically about beans today, but a whole range of crops. But the issue is the percentage reduction as the salinity goes up. And so a 10% increase in, so you can experience a 10% loss in yield for beans simply by moving from a salinity of, a 50% increase in salinity. The second issue is the sedicity factor. That continued irrigation with saline water begins to destroy the soil productivity and increases the clumping and the ability for the soils to be worked. Now, managing it with traditional membrane systems or traditional desalination is just prohibitively expensive. Reverse osmosis, those types of systems work well to supply large urban centres with water, but the economics do not work in broadacre or a lot of irrigated systems. The other approach is to do alternate irrigation where you use fresh water to leach out the soils, but that of course becomes very limited during times of drought. So the approach that was developed to deal with this issue was to take the elements of reverse osmosis, which of course is the reverse osmosis membrane, which is a pressure-driven liquid phase separation process where you overcome an osmotic gradient using expended energy in the form of discharge pressure from a pump to drive water across a membrane that is more permeable to the water than it is to the salt in the water. And I guess the innovation in this approach was that we were able to match that driving force required to pull water, or push water rather, across a membrane. In our case, we pull it. We were able to match that driving force with the matrix potential or the suction pressure within the soil structure that was induced by evaporation through the leaves. So what you're looking at here is a schematic at the top of the evapotranspiration process, whereby UV light hits the leaf, creates a tension through the stem, which is transferred via the root zone into the soil where the membrane is located. The plants that you're seeing there are actually tomato plants, but the experiments that we did were largely done with beans. And through working with a range of beans over a full growth cycle, which was approximately 70 days, where we track a range of variables such as the germination efficiency, the leaf gas exchange, where we're looking particularly at the activity of the photosynthetic centers of the plant, but most importantly, the water use efficiency and the yield. So how much water we are using compared to traditional forms of irrigation, and whether we were seeing a reduction in yield. So what we're looking at here is the cultivation of the beans over 64 days. So that's all the way through to a crop. And you're looking at two sets of data. The line at the top is the control, and the axis on the y-axis is the average soil water residual content. And you can see then the control is where it's irrigated under using conventional surface irrigation, where the water is introduced from the top and percolates into the soil. And over those 64 days or out to 70 days, the soil holds that water. In the membrane system, which is the light gray there, you can see it's declining, and it's getting down to almost to the point where you're at the permanent wilting point for the plant, meaning that the plant is really sitting in quite dry soil. But when we look at the results of comparing the control with the membranes, you can see that the membranes were able to still deliver water to the plant while the plant was evaporating, even though that the soil residual water content had fallen below that permanent wilting point. And if you look at the yield in terms when it's scaled for tons per hectare, you can see with we were looking at a yield of around about 4.8 tons per hectare with conventional irrigation, that was being reduced to 3.8 with the membrane style irrigation with a particular type of membrane. There are others that were less efficient. That's the one there on the right. The little letter after that number 4.8 refers to the statistical significance using a Tukey test, meaning that there really is essentially no statistical difference between the 4.8 and the 3.8. More importantly, if you look at the water use efficiency, we're up at around about 12.8 kilograms per cubic meter of water applied under the conventional, with the membrane irrigation, which compared to 7 kilograms per cubic meter of water applied for the control or the conventional irrigation. So the membrane irrigation was almost a factor of 2 more efficient than the control. It's interesting to point out that under good conditions, the typical commercial fresh bean yield is around about 6 to 8 tons per hectare. And the irrigated water use efficiency is only around about 1.5 to 2 kilograms per cubic meter. So this system has the ability to really maximize yield production while minimizing water input. And those points bear it out there. So we're really doing quite well compared to the standard metrics. When we begin to look at the effect of the membrane or the on the plant, we look at the total leaf density matter and the leaf dry weight, and again looking at significant changes there compared to the control. There was a minor reduction, but generally, if we begin to look at comparing the parts of the plant, the pod, the stem and the root, there wasn't really, with the good membranes, there was not a significant difference between the controls. That's the forward osmosis and the control. So we're comparing the middle bar and the black bar. Interestingly, root length is significantly different, and that's because the roots are really important in driving this process. The roots have to come into contact with the membrane in order to establish those connections, which allow the transpiration process to create the suction potential to suck water across the membrane. So you can see the differences there. The bottom chart there on the slide in front of you, of course, is the performance relative to the salinity. And so we looked at plant growth across a range of salinities, and we was able to see effective production of these plants in water salinities up to around about 3,100 microsiemens, which is around about 2,500 milligrams per litre of salt. And the graph that you're looking at there is the amount of water, the amount of salt that was transferred into the soil. So we're measuring the soil salinity at the end of the experiments. And so you'll see all the bars on the 0.2, 1.4 and 3.1. The two final bars there on the 3.1 are the systems that were irrigated using the membrane process. The other ones were the control and a membrane that was more porous, meaning it had no resistance to salt. So we were able to grow more crops the same amount of crop with significantly less water, but more importantly, we were attenuating about half the movement of salt into the soil. The final thing that we looked at was the effect of soil composition on the water properties. Sorry, the effect of the soil composition on water transport and plant germination. And so what we're looking at here is soils that range from a fairly reasonable sand and clay and loam content, which would be our good quality soils, through to soils that have a high sand or a more sandy type of loam, which traditionally are less productive for agriculture. And as you can see there, that on the right-hand side is germination percentage, which is the total number of seeds that germinate. On the x-axis, it's the increasing sand content. So what's happening there, that as the sand content increase, you get significantly less germination. As the sand content increase, the matrix potential goes down because the water holding properties of the soil go down. So you can see on the left-hand bar chart, left-hand axis is the decline in that evaporative water flux moving across the membrane. But what was quite interesting when we begin to look at this over a long period of time with a lot of data is that the soil becomes less significant in terms of water transport after around about 6 to 7 days of growth. And that's what the chart at the bottom there is showing, that once the plants do become established and can access water through the subsurface membrane, after around about 6 to 7 days, the soil surrounding the plant doesn't become as important. So what we're seeing there is that whether it's greater than 70% soil, which is the good quality soil, all the way down to 40% soil, which is where there's the bulk of it, 60% is made up with sand. After about 6 days, that effect is lost. And after that, all the soils, the water movement is independent of the soil structure. And you can have a look at the photo in the top right there, and you can see that the roots are really beginning to consolidate around the membrane. When we begin to look at the gas exchange, it begins to tell us how the photosynthetic centers are working. We tend to compare the isotopes of carbon, particularly looking at the differences between the C12 and the C13. the C12 diffuses more quickly into the air, and it results in less stomatal activity. Consequently, you tend to get a greater buildup of C12 in the leaves. Also the isotopes, higher carbon-13 isotopes, generally is associated with lighter mass, whereas more carbon-13 isotopes means it's more heavier. So we looked at that mainly to assess the health of the plants, so whether their quality. And so in general, we were getting, again, reasonable comparison between both the control and our preferred membrane, which is the FO membrane. More importantly, we were seeing a distinct response to diurnal variability. So as the sun comes up in the morning and you begin to reach peak transpiration in the middle of the day, we were seeing a distinct transport of water responding to those demands. So over the total cycle, we were looking at both the leaves and the pods, comparing the control with the subsurface irrigation, and we really weren't seeing a significant change, particularly in the pods, in the carbon-13. So we've been able to demonstrate that we can improve yield on saline water. We can use marginal quality soil, and compared to conventional surface irrigation, we can really increase the water use efficiency from an optimum value of 7 kilograms per cubic meter for really, really well-controlled surface irrigation up to about 12 kilograms per cubic meter of water applied. The initial germination, of course, is more sensitive to the soil hydration, so that's why it's hard to get seeds to germinate in sandy soils. But once they do, and they can access the water in the membranes, in the irrigation tubes, after about 7 days, the quality of the soil becomes less important. The plants cultivated on membrane irrigation produce leaf biomass and yield that was statistically equivalent. So the quality is not the same. There are some irrigation impacts on leaf gas exchange due to the additional resistance, but that can be mitigated if we pick the right membrane, which in this case was the forward osmosis type membrane. So this is an example of how we can manage water demand for plants and increase irrigation efficiency in the production of beans. And so with that, I'd be more than happy to take questions. So I will do the job now of both moderating and fielding questions. So let me, there we go.
Yes, Greg, I've sent you a couple of questions there, so feel free to select what you feel is suitable.
So we've got one for Valeria, and this, I'm not quite sure who the question was from, but Valeria, would you mind talk about the total irrigated area in Carnarvon?
So pretty much every farm is irrigated. Because of the climate, we don't rely on rainfall to irrigate the crops. And the total area, so if you think we have 170 farms, and the size of the farms range from 5 to 10 hectares. So all of that area along the river. So we have two main areas along the river, the south and north of the river, which those farms are distributed, and they rely exclusively on groundwater. So they have, it's groundwater, the river won't flow. If you come, you'll see just sand, but they infiltrate and you have that groundwater reservoir for them to pump out. And so they say they have a water resource available for probably 3 to 5 years if it doesn't rain or if the river doesn't flow. But they're mostly reliable on hoping that the river flows every year. So when rains in the catchment area inland, a couple of kilometers inland, then those rivers, they feed the Gascoyne River, which runs through Carnarvon.
Excellent. Okay. David, in terms of cropping precincts, or sorry, the planned precincts, you mentioned the Namoi Valley. Why was that area particularly important?
It's arguably the most productive region in Australia. It has very deep alluvial soils by Australian standards. They're up to 40 metres deep, excellent soil. Has quite reliable groundwater systems as well, which are not saline. So you've got good quality groundwater, you've got good quality soil, and that means they can get 3 or 4 crops a year, which is not typical of Australia at all. So in short, it's a highly productive region, but nonetheless it does face increasing water scarcity and the issues I mentioned. And of course, different crops are being grown at different times of year, and under our policy framework, water is allocated to people who have water licenses. So people own a right to share whatever water is available in a given period. With surface water, groundwater, of course, is very complex and hard to understand, particularly when the aquifers are connected in ways which aren't fully understood. Was that the question?
Yeah. And then the other question, David, is power subsidised for farmers in that part of Australia?
No, it is not. It's actually more expensive because the network charges are higher. Electricity pricing in Australia has a component which is the electricity cost and a component which is the cost of delivering the electricity, which is called the network charge. And in regional areas, farmers are accessing electricity that could have been generated 1,000 kilometres away, and it's been provided by our high voltage transmission network. So one of the arguments is that we should be generating electricity locally, which will reduce those transmission costs and potentially change the way we think about electricity infrastructure. As I said in my presentation, electricity is a reticulated system, just as is irrigation. And there are some wonderful synergies between those two systems if you integrate the engineering approaches. But in general, water engineers and energy engineers don't spend a great deal of time together. I think they should.
No. I agree. Okay, are we getting any more questions coming up?
I have a question for you, Greg, which was about the members.
Yes.
Fascinating research. But how do you deploy that commercially in broadacre farming, or is this only something that can be done small scale?
So we've run those numbers, David. I didn't put those slides up. It's hard to get. So let me answer that question in 2 parts. We've been able to demonstrate that the materials that are used in commercial membranes can be fabricated into these tubes that will allow, a statistically valid or statistically significant number of crops and treatments to be grown. We are not in the position to produce membranes at the university, so we just buy them, cut them up, and fabricate our own tubes. So we said, okay, if one was to purchase an equivalent amount of membrane at standard reverse osmosis membrane costs, so the sort of costs that you would incur if you were building a seawater desalination plant. So buy those membranes and then fabricate them into lengths with 2 metre and 1 metre laterals that you would in a conventional drip irrigation system. What would be the price differential per hectare? And we were out by a factor of 2, not trying to optimize the price of just taking a unit cost from another industry, which is the reverse osmosis industry, and then just saying, look, we don't want all those components associated with a reverse osmosis element. We just want the membrane. So throw away all the spaces, all the other material. On those non-optimized costs, we were a factor 2 out, which told me that if you were motivated to do this, you could come a long way down the price curve. One of the big issues that we've spoken with Murray-Abinji Irrigation and some other irrigators is the longevity of traditional drip tape. They might get 3 to 5 years out of it. It's made with a polythene, which is non-biodegradable. The best results that we saw that I presented there, that what was called that FO membrane, is made from a cellulosic material. And the cellulosic materials have got the best opportunity to biodegrade. The particular materials we're working with there cannot biodegrade because there's been some cross-linking of the cellulose groups. You have a triacetate group. But again, with manipulation, I'm very convinced that you could make that membrane material out of a cellulosic derived base that would break down in the soil after one crop. So I think it would be fairly cheap to use. You get a crop out of it. It would then break down in the soil. The biggest issue is you still have to manage the brine that comes out the end. We haven't, you're using saline water. So in a saline water application, you still have the problem of the salts, but in a freshwater where you're competing, if you wanted to maximize the yield that you could get out of limited freshwater supplies under the best quality surface irrigation at 7 kilograms per cubic meter, we would be sitting at 12 kilograms per cubic meter in a system that responds to evaporative demand. So it is a self-scheduling irrigation system.
Excellent, comprehensive answer, Greg. We'll talk about that afterwards because it fits the decarbonisation hub. There's a project there, I'm sure of it.
Anyway, sorry, I get somewhat excited talking about Valeria's former work.
Well, Valeria, the field could use that work, couldn't it?
We've got a.
Sorry.
That's right. We do have a question from Malaysia. So I'm from Malaysia. Some of the rice production is affected by brackish water. Any advice in terms of water engineering systems? Yes. So the Bruce Sutton, my colleague that is the agricultural scientist, has done a lot of work with the rice CRC and a lot of work through Indonesia on different rice systems. Bruce would advocate for if it's possible to alternate the use of lower salinity water with the more brackish water, if that's possible, to just let the soil regenerate in terms of the rice cultivation. There are also, and I think this work has been done, a lot of this research was done in Indonesia, there are some rice cultivars that have a greater tolerance to salt. And so you can begin to select for cultivars that do a bit better on the water. Valeria, did you, in your work, have you come across anything on rice? It's a pity Bruce is not on the call, and the effects of managing the effects of saline water?
No, not in flooded irrigation, which I'm assuming that's probably what they're using.
Yeah.
Because they're like managing the water would be like you said, alternating. If you find that a specific crop growth stage is being more affected by salinity, then cycling the water or mixing the water of good quality with a lower quality between stages, using a better quality on those stages that are more sensitive to salt, then you can switch to a higher salinity level as the crop establishes. That's one option. or mixing, but that is dependable if they have an option of better water quality to cycle or to mix. And then doing research on improving the efficiency of your water, like localizing application, that would be something apart from looking to tolerant cultivars that could be managed.
I'd be more than happy to take that question from Mohammed and pass it on to Bruce and see if he's got, because I know that rice was one of his specialties. I think that exhausts the questions, unless I've missed one. There have been general questions about will the slides be available, and the answer, of course, is yes, along with the recording, and IWRA will take care of that.
Exactly, Greg. So I think we managed to address most of the questions that were posed in the Q&A tool. And now I think we're approaching the end of the webinar, unless there are no further comments or questions from the panelists or participants. I think we can slowly wrap it up. And on behalf of IWRA, we would really like to thank Greg for moderating this wonderful webinar, and for Valeria and David for presenting